Thanks everyone. And as I said, it's a great pleasure to be today. I only have 165 slides. So all right. So it's a great pleasure to be here today. So thanks for hosting me. And I just wanted to start by just saying a few words about where I am at the moment. So for those who don't know York, it's that dot on the map. It's a small, relatively small city close to Leeds and Newcastle. And the middle, that's the Department of Computer Science. So it's a relatively new university overall. Only 55 years old compared to the more traditional universities in the UK. And something that I also like to mention is there is a newly built facility that we have at the university, which is called the Institute of Safe Autonomy, which is a 35 million building initiative around the making autonomous systems more safe. And why I mention that, because all these we see all this potential that AI can bring in a multitude of domains, ranging from healthcare, agriculture, avionics, name it. But also we need to, because we deploy those systems in these applications in safety critical systems, we need to make them safe, right? And that's so that they can be trusted, they can be trustworthy from the users, and they can meet some levels of dependability. They are reliable, robust, and resilient. So, and I highlight in the title the towards. And why am I doing that? Because we are a long way to achieving that. Unfortunately, there are very interesting applications, as we will see very shortly, but achieving trustworthiness so that it can be deployed and be beneficial for the users, we are still need a bit far from that. So just a quick intro in terms of my background. I did my bachelor in the University of Cyprus back in 2010, and a master in software engineering and computer science from the University of York. And I've been in York for a number of years now, for 12, 13 years now, initially as a postdoc, then as an assistant professor, and more recently as an associate professor. Now, as we have seen, there is a very bright future and a huge potential for making systems more autonomous, giving them the capability to cooperate with the humans. And as we increase the level of autonomy, eliminating the need of the human, not just because we don't want it to be so, we want the human to be involved, but because we want it to be able to do more interesting stuff, to devote their attention into the challenging parts and not paying attention to the dull or the easy to achieve activities. And irrespective of the domain that you will talk about or that you will focus, either it's a service-based system like your favorite streaming application like Netflix, or if you have robots helping nurses in a healthcare facility, or in this case, disinfecting commonly used areas and spots, or within a smart city that is being used in order to monitor, provide information about predictive maintenance, helping users to avoid traffic, or they help to make the environment smarter and reduce the pollution, or even within the Smart Farm Center of Excellence that is being proposed by the Cyprus Institute. You can see that there is a lot of potential in making those systems more autonomous, more intelligent, so that they can cooperate, collaborate, help users and the stakeholders, and enable them to devote their attention in making other more interesting activities. At the same time, there is all of this, one way or another, they use AI. And there is also a huge potential for AI as well, ranging from object detection to generating captions in images, making coloring black and white images, translation, if you go on a trip to a country where you don't speak the language, handwriting recognition, or adding sound to silent movies, for instance. At the same time, though, they have a huge potential to fail miserably, right? So unfortunately, I don't have the videos in this machine, but that's a very recent incident from two Waymo cars in Los Angeles. So this, the first one and the second one, and they are at the same intersection, right? And there is no, if you see the video, they try to turn right, but they don't negotiate. So the car that has a priority is one that is on nearest to us, but the other one behaves in a clumsy way and overtakes, making it dangerous to cause a collision, right? So these cars are driverless. There is no driver in the scene. Similarly, there are rescue robots. So you can see the robot here just about to fail, just about to fall. And also Amazon Alexa, which after, I'm sure you're all familiar with that, it started ordering doll houses after hearing its name on the TV. Automatic. And another very interesting incident is that there was a bias in allowing credit between a couple. They had the same credit score, they had the same account, a joint account, but the husband could take 3 times the loan than the woman. That was an autonomous decision-making system, right? And there are more examples as well of failures from AI and machine learning components in general. And the important point is that sometimes just adding some imperceptible perturbation can, either that is in images or voice, it can change completely the outcome of the machine learning model. And that has implications because, and for, if you have not heard of that, two very recent incidents from the very infamous ChatGPT and Gemini. So Gemini is a competitor of ChatGPT from Google. So ChatGPT very recently, last month really, was stopped for a while because it was hallucinating. And really last week, Gemini, as they call it, it messed up. So it changed historical images in such a way that it was not depicting or corresponding to reality. So for instance, here, this is representing 2 German soldiers of Second World War, which is, you don't expect to see a human, you don't expect to see this kind of appearance. I mean, there are many more examples, and really there is an AI incident database, which more than 3,500 relevant incidents about failures of AI. Now, as you might expect, because we deploy that in safety critical environment, either for making a loan application, for Amazon was using that in order to shortlist candidates for hiring purposes. There are some important implications, right? So we need to make these systems trustworthy, right? Before deployment and while during deployment. So the guy here, that's a tweet from Jack Kravitz, who is among the heads of Google's Bard and Gemini team. And they said, we are sorry about what happened, long story short, but this is part of the alignment process, iteration on feedback. Thank you and keep it coming. But really, is this what we expect? To deploy it and learn from our mistakes? That may be fine if you change the historical images of people and they don't, and the implication is not so serious. But what about if you deploy them in the driverless cars and they cause an accident? Who has the liability, right? Or if they, if you deny the loan from a couple who wants to buy a house. So these are some important implications that we need to take into account in order to deploy those systems in the real world and in the wild. So that's why behind this motivation, the research focus really is to building on theoretical foundation to develop techniques that allow us to do automated analysis, synthesis, modeling of autonomous AI-enabled systems, and reason about the uncertainty that those systems, they have a design time in order to make it more robust, and at runtime in order to enact appropriate mitigation actions. And as you might expect, this has a multitude of potential applications, ranging from data-intensive systems like cloud-based services, Forex, for instance, and robotic and autonomous systems. So the last one is a bit of my favorite. It's more as an application domain. So some of the examples that will follow, they would be mostly based on robotics and autonomous systems. But really, this is just an application domain, and the technologies and the techniques can be applied anywhere. Now, how do I see all this? Those autonomous systems, they, one way or another, they have a closed feedback loop. And there are many feedback loops that they have been proposed, but throughout the research, we have been using what's called MAKE, standing for monitor, analyze, plan, and execute. You monitor, you sense the environment, you get the raw data, then you analyze them, perform some classification, inference, localization, make a plan through decision making a risk analysis, or negotiate between what would be the best action to take, make some optimization, and then enact, make the appropriate actions in order to adopt the strategy, change the system configuration if needed, and then enact. Now, all this, in order to be applicable and you have a closed feedback loop, it needs to interact with the environment, irrespective of what that is. It may be a robot, it may be a smart city, it may be a service-based system running in the cloud, but it receives information, senses, and actuates on that. Now, if we put it in the ecosystem perspective and put the users into the mix, that is also the wider picture where we have the user interaction as well, through either this is the direct stakeholders, which they communicate with that autonomous system, or it may also be an oversight authority, right? Like a command and control center. So for instance, in the Waymo example, it may have been some operators at a command and control center overseeing how the cars behave, and they could take over if such a situation arises. They didn't in that particular case. Now, there are many challenges if we want to make these systems trustworthy. When we look at the wider ecosystem perspective, obviously we operate in an uncertain world where the environment uncertainty is everywhere, from the way that the stakeholders behave, failures in the and uncertainty in the operating, the decision-making components of the system itself, but also in the environment, right? You have openness and emergent behavior, news, the profile of the users who interact with the autonomous system, it can change. So it needs to learn and adapt to that, or the users themselves may change. We also have a variability. When we design that autonomous system, we may have different algorithms. Think about a computer vision algorithm. We may have different versions of the same algorithm. Which one do we take? Which one do we use, right? One may be more data hungry, another may be more accurate. So depending on our requirements, we need to make appropriate adaptation actions, right? And other words like other challenges like making adaptation, changing our strategies, our decision-making at runtime in a way that we ensure that our system continues to behave dependably, and making the systems tailorable, meaning that they should be able to provide the right explanations and understanding to the end users. Now, how do I see all this? I see all them as that we need to make autonomous systems we need to provide these autonomous systems or equip them with some very key features. They need to have a set of characteristics. The list is not exhaustive, but this is our, let's say, the four that I'm mostly looking into. We need to make them adaptive, as you might expect. They need to react to changes in the environment or the objectives. For instance, change the environment may change. They need to also be able to learn and proactively adapt to potential disruptions. Given that we want to be environmental friendly, they need to be green, as they call. So minimize the carbon footprint, but at the same time maintain appropriate and adequate performance. Trustworthiness is another key aspect. I highlighted that quite a lot. So we need to make decision making considering the uncertainty that is inherent in the operating environment, in the ecosystem. But they also need to be human-centric. They need to be fair, making the decisions in a fair and unbiased way. At the same time, help to be more explainable, right? So that users, they can understand why a decision has been made. Now, within the research, I've been, we talk about technical research strands. I've been partitioning my research in three. So uncertainty-informed reasoning and adaptation, safe AI, and simulation-based analysis and testing. I'll try and cover the first two, but I suspect that due to the lack of time, unless you want to stay until 4, we need to skip that for now. But I'm happy to cover that later. So in order to reason and make uncertainty-informed adaptation, we have a model of the environment, of the system that we're interested in, right? And how do we model that? Let's take a concrete example. Let's say that we have model a sensor of a particular system, where it measures, let's say, the temperature, right? And that sensor, so this is a Markov model, right? It's a graph, essentially. So that starting from state 0, that system can be, that sensor can be on, in which case it starts taking measurements, right? With a probability, with a particular probability, the measurement is correct, and it moves to state 2, and then it prepares to take the next measurement. With 1 minus p probability, pi probability, the measurement is inaccurate, as we call it. What affects that? That, for instance, a particular example may be, imagine that you are driving your car and you want to take a picture. If you are moving faster, if you are moving fast, the picture will be blurry, right? And so you cannot create a panoramic photo. If you are moving slower, then the picture would be of good quality. So you can stitch them together to make a panoramic photo. So that probability, it may be a variable aspect that depends, let's say, on the speed of the vehicle in this particular case, or it may be the surrounding environment. If the sensor can be off, in which case it just stays in an idle state. So we can, by changing that particular variable, xi, in this case, we can switch the sensor on and off. If we put multiple models of the same sensor, or multiple similar models, but for different sensors together, then we have a composite sensor-based system, right? That allow us to select dynamically which sensors to select and which sensors to activate or deactivate, right? So if we put all of this together, we end up with, we can model this as a probabilistic model. So this is a mathematical representation of the graph in the left, right? I forgot to say that the epsilon I, they correspond to the energy consumed when I switch on or off the sensor or when I take a measurement. And I also have some additional information. I want to capture how many accurate pictures I took or how many measurements I took. So this is a Markov model. I won't get into the details, but what that allows us is to, by having such a simple model, it allows us to check, let's say, what is the expected number of accurate measurements every 100 meters, which is a variable of the speed. And similarly, what is the energy that I can consume as a factor of the speed? What that allows us is to, by changing, let's say, the speed variable, which affects the probability, and the xi factor, it allows us to analyze the behavior of that particular system, considering our two requirements. I want to get an expected number of measurements per 100 meters, let's say. So that's just an example. And I want to keep my energy consumption at a particular threshold, right? So what that allows us is to tune the which sensors I want to switch on or off at a particular point in time and set the speed, for instance. And this also allow us to make this dynamic adaptation. So this is just a quick recap or a primer on probabilistic analysis. Now, just to make it a bit more concrete, assume that we have a robot which or a team of robots which they need to deliver an item from the service station to the patient's room, and they have two different ways to give that. Corridor A goes to the door, and corridor B, then you can go through corridor C. That's another possible route. But there is also some variability in those environments. And there may be people coming and going. There is a door here which it may be closed or open, and we need to devise a strategy. Do we need to send one robot, first one and then the other, send them in parallel? Would we wait for one to get, or to find out whether it's trapped or not, in order to optimize a set of requirements? Say the performance. I want when I receive an urgent request to deliver the medicine within 5 minutes, and I want the reliability that I will be able to execute the task, the delivery task successfully at least 99% of the time. As we mentioned, there are several uncertainty factors. And the question here, so at the bottom left, you can see a simulation that we have built in order to simulate that. So the question here is, how can we synthesize a robust strategy by selecting the best system parameters so that the system that the mission execution is optimal? Now, and here is the core of some of the work that we have been doing. So as you might expect with probabilistic analysis, it's a formal method which provides guarantees, right? It's precise, subject to the model being correct, of course, right? But it has scalability issues. Then we have a state space explosion. And it may be hard to use because you need some expertise in order to write that particular model. At the same time, we have evolutionary search. So the dimension, the space is quite large, right? So we need to find a strategy, and that may be fixing some particular parameters or in order to devise a strategy. And we can use evolutionary search, which comes with weaker guarantees. Because it's a search, it doesn't guarantee optimality, because you cannot search the entire space exhaustively. Or theoretically, you can do it if you give it infinite time, but most of the time that's not the case because you have a fixed budget. It's scalable, and it can support multiple objectives and constraints, which is typically the case in realistic scenarios. So what we can do here is that we can combine them and leverage the best of the two worlds. We can use probabilistic analysis to get precise computation, and evolutionary search to do targeted analysis, right? And if we put this together, that's a tool that we have built for a number of years now. We call it EvoChecker. And as an input, it gets, let's say, the constraints and the optimization objectives for the system that you're trying to develop or to adapt, a probabilistic model template. I'll show an example in very shortly. And through the combination of this probabilistic analysis and evolutionary search, it gets you back a set of a Pareto front and a Pareto set, which is essentially the policies, Pareto optimal policies that optimize that they optimize optimization objectives and satisfy the combination of constraints. And essentially, we transform this policy synthesis, this decision-making under uncertainty problem, into a multi-objective search problem. So that's what happens under the hood. And so given these particular inputs, what we get there is a parsing of the template that takes place. Then there is an iteration that happens, trying to identify the best set of strategies, the Pareto optimal set of strategies. And these, they can be used later on for the adaptation of the system. So how does a probabilistic model template looks under the hood? It's the typical probabilistic model with some additional constructs that essentially denote the knobs that you can turn, the variability that your system has. What are the options really? And this can be a particular sensors, let's say, in the example that we are saying, or different robots. You can change the distribution that they make a decision, or we can also change some discrete parameters that they may correspond to the capacity of a system of, for instance, in the particular case, how big the set of tasks it can handle during that particular period. So what it allows you to do is that to examine efficiently the potentially discontinuous and not convex policy decision space, which is typically the case when you model systems in such a way. By using evolutionary search, we can focus on interesting areas of the policy space and essentially allow us to identify this case of the points of diminishing returns, essentially where it's like the sweet spot in the decision space. And the other interesting part that we found out is that because it's a search-based process, but it's a population-based process, it also allows you to find in the objective space, which is this, you can have multiple equivalent in the objective space solutions or strategies that they achieve the same objective, but they have different decision points. That allows you to switch them if one fails. If one component used in one solution fails, then you can switch automatically to the other, but without making any additional search, right? Any additional analysis. Well, because we have, in many cases, there is, let me see if there are distributions, right? So in the examples that we run, we consider the distribution up to the, I think, third decimal place, right? Or each double parameter up to the third decimal place. It was something up to the power of 60. So the decision space, the entire Cartesian product of the decisions. So I think it was up to 20, 25, something like that. But there is no limit to that. Why? Because the benefit of using evolutionary research, I mean, or genetic algorithms, you can, for instance, right? It can be as large as you like. So in a different context where you used again evolutionary research, it was much, much larger. So it was, I think, exceeding 100 points. Well, of course, the higher the dimension, the more time is needed in order to converge. So we have used that in order to mission planning policy synthesis for various types of Markov models, discrete time, continuous time, and Markov decision processes. Another interesting part of the work was that we used it in order to do sensitivity-aware policy synthesis. So essentially, it gives you a set of solutions, but they have different sensitivity, different robustness. So the red here, it denotes they may have a better trade-off, or they may be at the sweet spot, but they are very sensitive to variations in the environment or the system operation. Whereas some at the bottom right and top left, they are smaller, which indicate a more robust plan. They can withstand more variations in the system operation. And that someone can choose between the two, whether you want the sweet spot or some that they may have a lower quality attribute, one in this case, but they are more robust. And they also apply that at runtime in order to enable dynamic adaptation. In this particular case, in order to make the search more efficient. We used an archive in order to essentially to seed the search, which was proved quite useful and time efficient. Now, in terms of applications, it has been applied by us and colleagues in a number of application domains. For instance, in order to make a plan for a mobile manufacturing cobot, to derive the mission for the teleassistance system, which was delivering a drug service. That's in simulation, just to be clear, right? And we used an open source exemplar that was available for the validation, and also by some other colleagues in order to inform the decision-making adaptation in an automated lane keeping system, which essentially here it was combining a mandibular network module that analyzed the driver attitude or state and sensor information from the car, making a classification about the attention level, and based on that, it was making a decision making a runtime whether to alert, ring an alarm, or to inform the driver to take actionable, so to make action. Now, because we realized that, coming up with a template and getting started with this is quite challenging, because as you might expect, putting together this template might require some expertise, which is, it requires a bit of time. It's not rocket science, but it requires some effort. So we have recently started to develop a technique that allows us to automatically derive those templates from activity diagram or UML diagrams. So which are more familiar for computer scientists, at least. So you specify the behavior of your system as an activity diagram, and then automatically translates that into the template and makes a synthesis, so that it uses the entry point for users. Now, moving on into how we combine this with learning. So a similar example is a sensor that we have earlier, but now we have, let's say, a robot again that is interested in inspecting and cleaning some chains. Again, it's a graph, right? And we represent each chain, a very simple abstract model as such. So the robot is approaching the chain and is inspecting the chain. If the chain is clean, then we move to done. If the chain is not clean, then we need to clean it. So that's inspired by a European project which was using UUVs in order to clean offshore wind farms. So, and the co-authors, they were involved in this project. So if the cleaning is needed, then you try to clean. As you might expect, it can fail. If it fails, you need to prepare again to position it. The UUV needs to position itself in the appropriate location, retry, and make a decision there whether I will retry, and if I retry and I clean it, I go to done and move to the next, or I abandon because I won't be able to return back, or I won't have enough energy to move to the other chains. And the same story applies for the others, right? Now there are various points that are uncertain, right? They depend on the behavior of the environment, and that may be how much time do I spend, what is the probability or the rate in this case, because we are talking about continuous time, that I will spend in order to inspect the chain. If the chain will be clean or cleaning would be needed. And also that is always the case that because I need to try and deploy the system in a safety critical environment, I may collide with the chain that I'm trying to, or I may essentially damage this system, right? So some of those parameters, like the blue, those that are in green rectangle or rectangle, they are unknown, right? we cannot know them at design time. We need to monitor them and measure them, quantify them at runtime, right? Because that depends on the operating environment. So some of these events, like the blue, they are regular events. They happen frequently, right? I may try to clean it. I will fail, right? And I need to prepare myself. But I don't know how much time, what is the rate of failing, or how much time I will need to reposition myself, right? And obviously, some other events like damaging, they are singular, they're catastrophic, right? If I damage the UV in this case, it's done. If I collide, it's done, right? So the question here is, how can I obtain accurate internal estimates for these events at runtime, whether they are regular events or whether they are singular events, right? And what we have used here is Bayesian techniques. And the first, we developed two estimators. One is called BIPP, Bayesian inference with partial priors for singular events. Essentially, here, instead of representing each rate as a Poisson distribution, we can use the Bayes theorem in order to extract the posterior data. What we have developed here is a technique that allows you to get intervals of the singular events in this case, but without the need to define the full distribution of the prior. You just give limited partial knowledge, which essentially come in the form of confidence bounds, where epsilon are the bounds and theta is the probability. So this is your prior essentially, right? And I won't get into the math here, but depending on how strong the epsilons are, so essentially it's like I think that I think that the rate is within this bound with that probability, right? So that's my prior. And I can give up to, or I need to give at least 2 bounds. And there are the mathematical formula here, which but essentially what it gives you, it's the interval, right? Of the lower and the upper bound. And what that allows you to do is that it allows you to incorporate time. An important point here is that there is the notion of time. And as we leave the mission running for longer, the bounds become narrower until they reach their asymptotic bounds. And that asymptotic bounds depend on the priors, right? And the dots in the example, they correspond to the points where the cases change. For instance, in this particular case, we go from the upper, there are 3 different cases, and that's why we have the bullets, the red bullets. So where we move from one case to the next, and similarly for the lower bound. Now, depending on where the probability mass is accumulated, right? There is a different behavior. So here on the top, you can see that we have we allocate more probability mass is given to the lower bound, and the bound, as the time increases, it becomes narrower. At the beginning, though, because we allocate more probability mass to the lower bound, the probability to the lower lower bound, the probability is lower if we compare it with with the bottom half of the graph, where more probability mass is allocated to the upper bound. Again, here is the same scenario that as the time progresses, because we have not seen any catastrophic failure, and we have not that event happening, there is a decrease in the interval, which essentially leads to reaching that asymptotic bound. There is the corresponding element of estimator for the regular events. Again, starting from the traditional likelihood function and the Bayes theorem, we can have the posterior, which is for a single point, which is essentially if you exclude the prior, if T naught and L naught, which correspond to the prior knowledge on the time and the rate, that the second half will be essentially the average, like a maximum likelihood estimation. But now, if we give ranges for the prior knowledge on the time, lower and upper bound, and the rate. So I am essentially, I'm saying that I believe I'm that confident based on my prior knowledge, and the strength of my confidence is the T naught, that the rate is within that bound, right? So this is what we're saying. If T naught is 0, then we don't have any prior knowledge. If T naught is above 0, the higher the number, it corresponds to how strong is our prior knowledge, and L naught is the width. Then based on that, we get a corresponding interval for the lower and the upper bound for regular events, right? And what that allows us is that we get a similar set of equations, a similar behavior for regular events until they reach their, let's say, their estimated value or the actual value. And in the first row, we have cases where we have different strength and conformance to a different strength of the prior knowledge, but where the prior knowledge includes the actual value, right? Because we say that if I want to buy a BMW, I need 1,000 pounds. No. So my prior knowledge contradicts the actual, right? In this case, my prior knowledge aligns, conforms to the prior knowledge, to the actual value. So you can see that it's very quickly, depending on how strong the prior knowledge is, it approximates the actual value. And the stronger the prior knowledge, the more time it needs in order to narrow down the interval. In the two bottom rows, we have contradictory prior knowledge. What that means is that if I believe that I need 1,000 pounds to get a BMW, for instance, or I need 500,000 pounds, I contradict from above and below. And depending on how strong the prior knowledge is, the more time I will need to restore it, right? So that's what this estimator tells you, allows you to do. And how do we put this together? So because in the example that we discussed, we have that particular model that allow us to make decisions about the system, whether to continue to retry cleaning a chain or to move to the next one and so on. We have regular events, which we estimate with the IPSP estimator. And we have singular events, which we estimate with the BIPP estimator. So that gives us essentially intervals about the unknown rates of the system that we are interested in. Then we feed this into a Markov model, like the graph that we showed earlier. And by using a probabilistic model checker, what that allows us to do is we get intervals about the properties of interest of our system, right? We don't get point estimates, we get intervals about the reliability, the response time, and any utilities that you specify in your models, right? So we give intervals in as parameter estimates, we get intervals out. And this is quite important because we just don't base our reasoning just on point estimates, but on intervals, right? And this is more robust in this case because making decisions based on point estimates, it's quite sensitive to changes. So something else that we have recently done in the reasoning under uncertainty is that we have developed techniques that allow us to optimize or make the analysis more efficient by using conventional software engineering techniques. So for instance, we used caching in order to cache recent results, hoping that you will be able to use them in the near future if the environment is relatively stable, so that you don't need to rerun the whole analysis again. So that's a very straightforward technique. Limited look ahead. Essentially, the core idea here is that changes to the environment and all the aspects of the environment that you are interested in are typically localized. So if I have idle time between my decision making, I can search my surrounding area and see whether I can pre-evaluate this in such a way that when I need to make a decision, I would have already calculated my policy or my strategy. And the final one is nearly optimal reconfiguration, which essentially says that I don't need to find an optimal answer. I can find one based on historical data and the decisions that I have made so far. I'm happy if I reach, let's say, an X% of my historical data, and I'm fine with that. So you trade optimality with efficiency in this particular case. And this suite of techniques, it has different trade-offs between CPU usage, memory, response time, and whether the solution is the decision and the policy that you formulate is optimal or not. Good. I'll speed up a bit for that. And I think I've got, yeah, like 10, 15 minutes more. I think yeah. Yeah. So the other part is on safe AI. So because we're using AI quite a lot, and I like it. I use it as well as part of our work. But we want to make it safe. We want to make it trustworthy. We want to be able to reason. I'm a computer scientist, so I want to be sure that when we deploy something in the real world, it's as safe as it can be, right? So what we have been doing in this line of research is developing a set of techniques that allow you to scrutinize essentially deep neural networks and in order to be able to have a bit more information or confidence that when they are deployed in the real world, they are operate as expected. And they partition, the techniques are partitioned in design time and runtime. So at design time, we have developed a set of, given a data set, right, and your trained model, and based on the principles of conventional or how a system will be developed and evaluated. So we have developed first a set of techniques that allow to do white box and black box testing for neural networks. Essentially try to see whether you have tested your neural network enough so that you can be sure about its behavior or have some additional confidence about its behavior. And then if you don't have enough evidence, then you need to augment your data set in such a way that you can increase your confidence. So generate more data and give it back and test it, right? If you are happy, then you can deploy your system. But at runtime, because you may encounter situations that you have not seen during training, you need to be able to supervise those systems, right? So that you have some confidence, so that you can raise the alarm when the neural network's accuracy or the prediction is something that it's because of an input that it has not been seen during training. So there are a number of techniques. I'll cover them briefly, but so the first one is the question that answers this one is a white box testing technique. So essentially what we are trying to do here is to find, let's say, suspicious neurons in a neural network that they may be responsible for unreliable system behavior. So essentially we scrutinize the internal workings of a neural network. So if you see this one on the top left, and the idea here is that you want to, based on a principle that is derived from traditional conventional software engineering, that from what is called fault localization. So when you are having a test suite, you run your system, right? And we're thinking about lines of code. Some of those codes for any test, the test either passes or fails, right? Some of those lines of code, they have been executed. And you can keep a trace of for each line of code, how many times it has been executed, and how many of these times it passed the test or it failed. And this is called the spectrum. And based on that, we can apply fault localization from in conventional software engineering. In a similar way, we can apply the same principle with neural networks. If you get the test case, the test suite, you can perform spectrum analysis for the neurons, essentially run the test suite, keep a trace of which neurons they have been activated and inactivated, contributed to a successful classification or not. This is what we call a neuron spectrum. And then based on that, you can identify what we call the suspicious neurons, right? And based on those suspicious neurons, you can synthesize new inputs in order to scrutinize more these combinations of neurons, right? So this is what we have done in this particular line of research. In another one, again, in a similar way, a white box approach. So the underpinning principle here, or the question that we're asking is, how well have you tested the important neurons of a neural network? And the underpinning principle here is that when you get the value of a neuron, right, the neuron activation value, it has a difference with how much the neuron has contributed to the decision making. And most of the time is less, right? Occasionally it may be the same, but most of the time is quite less. And why is that? Because if you think about it, when you calculate the value of a neuron, it then through the weight, it can become smaller, right? Because of the activation and the weight values, but it may not have contributed that much to the final decision making, to a correct classification. So if you, in this particular case, what we have done is that we use concepts from explainability, right? Essentially, you try to scrutinize if we take a simple example, which pixel they have contributed, they were the most influential, so that the neural network classify this as 6. So what we have done is that it can also back propagate that and identify important neuron of your neural network, essentially those neurons which they contributed more for the decision making. By identifying those important neurons, then you can do targeted testing for those particular neuron combinations, right? You can synthesize new data if you have not achieved the desired coverage, and that they target those particular neurons. In a similar way, the concept here is again, we want to test our neural networks, but the principle here is that we want to be able to make sure that, the underlying principle is that when we deploy our neural network in the real world, we are not expecting to see exactly the same data as you have seen during training, but the expectation is that the neural network will be able to generalize, right? So we want to be able to identify in this particular case neurons that they can transfer to a similar domain. They can operate adequately in a similar domain that is not the exact domain that it was seen during training. And what we can identify by doing this analysis, what we call transfer knowledge neurons, that they can operate adequately when they see near out of distribution data, which is not the same as the data that it was used during training. Now, by identifying those neurons in a similar principle as before, we can do targeted testing. And why? Because we can analyze the adequacy of the transfer knowledge neurons. So all of these, they are complementary. These 3 techniques, they are complementary, and they allow you to test different types of neurons for having different set of inputs. Now we talked about the augmentation, and we have been using. So you use these testing techniques, right? You are not satisfied with the results that you get. You need to generate more data, right? And how you can do this? Data augmentation. And there are many techniques about data augmentation, especially for images. And something that we found out in some of the projects that we have been involved with is that some of the techniques for data augmentation for images. They did simple geometric transformation, like cropping, rotation, translation, or trivial color space transformation. But more all of those, they did labor-preserving modifications. Of course, research evolves. But what was striking us was that you could do a bit more than occlusion. So you could also try to merge objects or try to change the kind of the image itself, but without changing the surrounding environment. So for instance, here you have a human, right? And you want to have occlusion, because in this particular case, an example from one of the partners that we had was that they were using a robot within a hospital facility in order to disinfect hotspot areas. But the problem that they had is that there may be the customer or patients or nurses, which they may be hidden behind doors, or they may just walk in and they may be occluded or behind some other people. So they are computer vision algorithms. They had some issues, primarily because they didn't have in their data set this kind of information, right? So it was difficult to collect this data. So what they did, what we did here, what we thought is that, okay, can we take these images and generate synthetic data in such a way, but without changing the surrounding environment? And we came up with a technique that uses generative AI, gets as input a set of seeds or an input, then we call this semantic data augmentation, because it can change let's say the key part of the image, but without changing the surrounding environment, and uses generative AI in order, I think it would be easier if I show this. So starting with an input seed, so that's from two different data sets, the Coco and the Lips data set. You can create the mask, and then you can generate different images. Then we do a fidelity analysis step, because we want to keep only those which they pass a fidelity threshold. So for instance, and the fidelity is based on various metrics based on computer vision. For instance, this one is this may be a bit more evident. This is an invalid because it's missing a leg, where all these are considered valid. So how we can use this? We can use this because they can either to augment the test set and rerun our testing for the neural network, or use them for retraining the neural network, right? In order to increase its accuracy. And it was also applied in some partners from in a European project in order to do data set documentation for their vine plants. So we get as inputs some original leaves, perform masking, and then generated additional images with using generative AI for diseases in this particular case that they may have not had the capability to collect data for, right? So this is, for instance, it's called Isariopsis leaf spot disease, and the company didn't have data for that particular disease. So, and we also try to do this for entire plants, given the original, generate the mask, and produce. Unfortunately, that didn't work very well for reasons that are quite clear, in the sense that there is the overlap is quite, on the leaves, it's quite substantial. So we were not able to keep, let's say, the environment as it. There was also some non-determinism in the generative AI, and the newest versions of Midjourney, Stable Diffusion should be able to do better. And the final, right? Because we also talk about design time now. So we have runtime part. So you do the testing, you do the data augmentation, you want to deploy your system in the real world, and then you want to make decisions, like what we are doing earlier with the decision making for the UV cleaning a chain, or the robots delivering some items in the hospital environment. Now, the thing is that you should not take the decisions given by the neural network as correct. You need to quantify its uncertainty, right? And in this part, there are various techniques that have been proposed in the literature on how you can quantify uncertainty. One particular example is dropout. Essentially, how dropout works, you have your neural network, and at inference time, you randomly disable some neurons, and you get the output. You do this a number of times, right? And then your result is the average of this, and the standard deviation gives you the uncertainty, right? So what we have seen here is that that in principle, the variance is high at the beginning, but over time it converges, right? So we don't need to do, dropout was done for let's say a next number of iterations, 1,000 iterations. But you don't need to do that. You don't need to do 1,000 times because it takes a bit of time. You may be able to stop early as soon as a convergence threshold is reached, right? And this is what we done. That's the first part. So we call it adaptive MC dropout. As soon as the convergence for all the classes that you are interested in is below a particular threshold, stop. Calculate the metrics and carry on. The other part, which is called conformal prediction, and the idea here, it's similar to, it's a frequentist counterpart of uncertainty quantification. The idea here is that you split your data set in your training, your calibration set, and your validation set or your testing set. You have your calibration set, and you calculate what it's called the conformance score, right? Which is essentially like a threshold, which tells you how uncertain is your neural network on the calibration set. And that's a very high-level explanation, but I'm happy to give more, to discuss it more. And the idea is that at prediction time, you have that threshold, and any class in this particular case that exceeds that threshold is collected and given as an output. So that allows you to not just give one prediction, but a set. And the more uncertain is the neural network, the larger the set will be, right? And this is based on comparing the uncertainty of the network with the calibration set using the conformal score, and by using it as a threshold for the during prediction. And that allows you again to get multiple outputs when the network is unsure. So what we have done here is that we combine these two, right? Adaptive MC dropout and conformal prediction in order to get both for classification and regression, in order to get not just the prediction sets, but also the uncertainties associated with this set. And what we have found out when we compare it with state-of-the-art uncertainty quantification methods for neural networks based on conformal prediction is that if we consider the red bars and the turquoise bars, so they correspond to the singletons and the percentage of singletons. So whenever the prediction contains only a single item, so it has it gives a higher number of singletons, but it gives this essentially when it's more sure compared to, let's say, the state of the art, which is RAPS. Whereas when it's unsure, it gives you an increased number of classes that is more than outputs that is more than one compared to the other one. So essentially, by using this combination, it allows you to use the uncertainty as an additional metric in order to give higher number of singletons, which are accurate, singletons only when you are accurate, and if you are only when you are sure, very sure that it's a correct answer. Whereas if you are unsure, you give predictions that are of higher, they have more than one class. And that's the same case with when we compare it with the state of the art in quantile regression. So whenever it's unsure, essentially it increases the interval. And that allows you to capture the actual value within the interval compared to the conformalized quantile regression and other techniques like the conventional Monte Carlo dropout. So what that allows you to do is essentially to scale up or down depending on the uncertainty. And you include the values that the actual values within the prediction interval more than the other techniques. And I think that's it. As I said, there is another line of research which I won't cover because I think we are overrun. Yes, and that's it. Thank you.
Hi, thank you very much. Very, very interesting seminar. I was wondering whether you have at the university some innovation hub where you valorize on this research together with industrial partners.
Good. So there is always a possibility to exploit this research or to apply this research in industrial settings. So there are the university, or at least York, actively looks for that, but it's more like a mutual, if there is interest from industrial partners to use this research. And there are, at least in the UK, there are what's called knowledge transfer partnerships, KTP project, which essentially allow you to take a TRL3 Polish research and then apply it to an industrial setting, and that is co-funded by UKRI in this particular case. But because in this instance the company would need to chip in to give some money, they need to be sure that they will have value out of that. So, and it has happened. It happens quite a lot. But and the other is through research projects like European projects where people are involved, try to deploy this in industry.
Thanks. Any other questions? If we don't have any other questions, let's thank Professor Gerasimou. We can continue outside with snacks and drinks.
Okay, thank you.
Thank you.
Show the slide the singular it's a regular event.
Oh, sorry. Okay. That one. That is it. Okay.
I wasn't sure about the show make it nice.
No, that's fine. That's fine.
So basically, as the time passes, what happens to those thresholds? They get bigger or smaller, right?
So that's the time, right?
Yeah.
So I mean the assumption here, because that's for illustration, is that the truth value, the ground truth,
Okay.
it doesn't fluctuate much.
That was my first. Okay.
Yeah, I mean if it fluctuates, of course your bounds will need to accustom for that, right?
Okay. Yes.
So that's if it fluctuates, then your because of the calculation here, you get the actual value, right? You calculate how many times have taken that position, right? So you're able to accustom that to take into account that. But if here the scenario was it stays approximately the same, right?
Okay. Yeah. So and then it converges.
Yeah, I mean, the stronger your prior is, the more time it needs to converge.
Okay.
So the vertical lines, right?
Yeah.
It's the how strong is your prior. So initially it's very informative. So I don't have any prior. I have no idea. This is a very strong opinionator. So it has 1,500.
Yes, it's very local and it takes time to.
Yeah. So this is a very strong prior. It's wrong in this case. So that's why I say that it's not very clear. It says that the green one, which is this, says that I believe that my prior, based on my knowledge, the upper bound and the lower bound is between 0 and 1. Right. So that's
Like
1 and 0.
You want to get to 3.
You want to get to 3, but because I'm very strong opinionated,
Yeah.
so the higher the T is not, the larger the stronger the opinion. So I need more time in order to adjust my value, right? Whereas this says, I believe that it's the same between 0 and 1, but I'm not so sure. I have a high strength in my opinion. So it becomes big, right?
Yeah. So just trying to see what's the difference in the flow.
No, that's the same. That's the same.
That's the same.
That's the same as this. The only difference between the greens
Yeah.
are the how strong they are.
I'm still.
So that's 75 to 125.
I was 75. Okay. Yeah.
Right. So these are how strong it is. So that's an informative, mild, medium, strong.
Okay. And these are not uniform priors, so basically it's boxed within the thing, right? These are the other thing with the partial thing. I haven't seen that before. So I'll go along with the Bayesian stuff.
Okay.
I haven't seen so your
So
the next one.
this one.
It's a partial priors. Okay, partial priors. Okay, that's the one. Okay. So here, so this is like a uniform prior. So basically, you have steps of uniform priors.
Yeah.
Okay, that's fine. And then you move to different, and then you, and then that's the thing you move along. Okay, right. Yeah, so okay, so basically you have steps. So you go like each box is kind of like each with plus different probability. And then okay, that's interesting. And is it biased like in practice, right? Because singular events they only happen once.
Yeah.
How do you think?
That's a good point. So that's why in the example we
Yeah.
only use that for the catastrophic thing. Because once you break, you broke, right?
Yeah.
But it's like things that you want. So this is not used in isolation. It should be used in such an example where you want to minimize. You want to make a proactive action when the threshold of damage approaches what you
Okay.
right.
I got it.
So you don't want to see that, but
Yes.
it's a part of your system, right?
Yeah.
So essentially, it's saying that initially, I have a very high bound, but if I don't see that over time, I will reduce the threshold up to this asymptotic bound. So that it won't reduce any further.
Right.
Because of the math under the hood, they reach that asymptotic bound if that's the case.
Right. Oh, I see. Okay. Yeah. Thank you.
So initially you have a high. Initially you have a high. The bound is high, right?
Right.
And if you want to be conservative, you will use your upper bound. You want to be optimistic or risky, you will use the lower one.
Right.
Or I mean, you can also use it pepper. But essentially, usually you say that it's high, but as I don't see any failures, I reduce it up to the asymptotic bound.
Okay.
So that's the idea. Instead of,
Yeah. I got it. Yeah. Okay. That's really good. Okay. And then you move to
and that depends again, here it's where you allocate the probability mass, where it's because essentially what we are saying here in these functions is that I believe that it's between epsilon1 and epsilon minus 1 and epsilon1. So it's like say you have it can be anything to this. I don't have the numbers for the examples here, but it can be anything, right? And you say, I believe that the rate, where the rate is this rate, right?
Yeah.
Of having a damage
Yeah.
is between epsilon minus 1 and this without probability.
Right.
So you're saying it's within this box. I believe that it's within this low rate and this rate within that probability, right? And that's how you construct your partial
Right.
values instead of giving the full distribution.
It's like it's another thing like it's almost non-parametric. Is it?
Kind of. Maybe.
Because you kind of like it's not built in your distribution. You
Yeah.
kind of have these
Yeah.
things like these
Yeah.
boxes. And,
Yeah.
And
And then, I mean, the theories are in the paper. And so you come up with these formulas. And that allows you, because it takes into account the likelihood, where the likelihood is based on, let's say, the time, or
yeah,
there, then that allows you to lower the bounds until you reach the asymptotic bound.
cool. Yeah, got it now. Sorry, I just.
No, I think it's quite neat. It's quite interesting. But the point here is that of course you can use it to monitor a single rate, right? But it doesn't make sense in reality because you also need to put it in context with the wider scenario.
Yeah, it's a standard thing, right? You're trying to model singular things, you always have to kind of like have a bit of an effect.
Yeah. And the interesting part here was that we put it in context, so you get intervals, you get outputs, you get from those estimators intervals, and you pass them into an interval model check. So you give intervals for the unknown rates, and you get intervals for the properties of it.
Yeah. Okay. And then the controller does have an optimization.
It has an optimization. I mean, I didn't spend too much time here, but essentially here it says that for that's the reliability, energy, and decision. So you say initially the reliability, so that's the various configurations. So the knobs, let's say those decisions. And you pick the one so that's a threshold, right? And you pick, let's say, the first one. Then as you do a second of them, because you have failed, right? The interval increases.
Okay. All right, but yeah.
Right? You are more reliable, you are less reliable, right? And here the interval increases as well. So if you compare the same point,
Yeah.
from this, you can see that very good. Yeah. So that's a key part of this for multiple attempts because because of the approximation that's happening, it increases the interval, and that essentially allows you to exclude, let's say, in the third attempt, these three, which they exceed the threshold, the energy threshold, and pick that up. So.
Okay, so that's the red zone. So
So the reliability remains the same. The energy is reduced as you try again because between efforts you consume your answer, right? It's like I try to turn to the 360. I don't manage the first time. I spend some gasoline. Try again. Now I have less gasoline now, right? At some point, I don't need to. I can do a 3-point, for instance. Later on, maybe I just go to a whole 360 of the CYI, so that I don't have enough energy, let's say.
Yeah.
So I don't choose this option. I have to choose one of the remaining. But I guess the key point here is that you give interval. Simple, you get intervals.
So you get the intervals here, so
yes.
You know where you.
Yeah. So that's the idea.
Yeah, no, that's really good. Yeah, it says.
But I mean, the application is in robotics, but the thought it can apply to.
Yeah, the idea is always the same. No, thank you. Yeah, and the parameters is just the the base and it's just a lambda.
Yeah.
The rate.
Yeah. So there's the parameters for that is the priors. It's it's a very simple mathematical equation.
Yeah.
So it's for the IPSP, it's these two, and you apply this, right? This function. Essentially, you're saying how many times I have seen this transition occurring within that period of time. So this is what you mentioned.
Did you try to like say make that lambda here like a function of other things in the system?
So it was no space.
Okay.
No, I think it's something that else that can be done, but it's
Yeah. We had for a different thing where it's like a completely different application, but you had like a kind of like a distribution there, and then you can model that as a, you know, you have various things in the system, right? I don't know what things you have in the system, but
yeah.
and then
That's
that becomes a model, like a free function, like a function of other things.
yeah. I mean, if you think a complex cyber-physical system, it can be, you know,
Yeah.
a function of functions.
So it could be like a thing like a physical parameters you have into your system that you want to put, like the things that would affect the failure.
Yeah.
Right? Say, I don't know, say the weather or these things, and then you could put them, you could put them there. Okay,
What's your name?
Leonidas.
Ah.
Yeah. Hemos aquí una premia. Perché tu da un schermo che tu la stanche kai, mo τώρα έφτασε και κομπρί, δύο μήνες.
Πού είσαι?
Στο Portsmouth.
Οκ. Τίποτα, είναι κάτω, είναι πολλά, είναι ωραία.
Είχα σε θάλασσα, ναι, είχα στο Γιώργο ήρθα.
Εντάξει, λίγο μακριά φανταζόμαι.
Στον Τάρο, είχαμε συνεργάσεις στον Τάρο.
Δεν μου κάνεις.
Εμείς ήμουν αστρονόμος.
Wow.
Δεν πήγαινα στον Τάρο, αλλά έκανα μια Bayesian. Bayesian. Αλλά μετά έγινα data scientist και έμεινα στο Portsmouth. Και τώρα ήρθα στην Κύπρο σαν associate research.
Ναι, αλλά ότι νομίζω τούτη τη δουλειά να ξεκάμαμε την με συνεργάτες. Αλλά βοηθώ που είναι καλό. Αλλά κάποια που τα μαθηματικά ανταρκίνη έγιναν hardcore mathematicians. Πριν, ξέρω, νομίζω το 2010, 8-9. Οπότε, ενώ ένα application, καλό application και extension του research, για probabilistic models.
Ναι, κοιτάξτε το.
Δεν το paper, νομίζω πρέπει να είναι open source, αλλά αν έχεις, αν το θέλεις να σου στείλω,
Να ψάξεις εσύ να σας αρέσει το μετσάσκι να φορέ τις applications σε μένα, βάσει Bayesian.
Αλλά είσαι Bayesian.
Στην αστρονομία δυστυχώς κάνουμε μας έτσι. Ξέρεις,
Γιατί?
Ξέρω, δεν κατάλαβα ποτέ γιατί. Νομίζω επειδή είναι